In this question here, right, we're told that in SA, the transportation of goods by trucks adds to the traffic problems on our roads. Now, a 10 kg truck, né? So you're given a 10,000 kg truck is traveling up a straight inclined road of length 23 meters, as you can see here, right? And it's traveling at a constant speed of 20 kilometers per hour, right? The total work done by the engine of the truck to get there is 7 times 10 to the power 5 joules. That is the total work done. And then the work done to overcome friction is that, right? Then now they want you to calculate the height h, right? The height h reached by the truck at the end of the road, right? Now the first thing we should realize about this problem, right, is that you are not given the angle of the incline. Okay, if you had the angle of the incline, this would be quite simple. Why would it be simple? Because you would have a 90 degrees here, isn't it? So let's say that you had a 90 degrees here, right? What would you do? If I knew that maybe he had 60 degrees, I can use maybe sine, right? I can just say sine 60 degrees would be equal to h over that 23, okay? Then in that way you'll be able to get the height, okay? So that is one way of getting the height. But now the problem is that we don't have the angle here. You're not given, isn't it? So yeah, it's gonna be a bit of a problem. And maybe to find the angle again, you could maybe think about FG parallel and FG perpendicular, right? But when they say the total work done by the engine, what do they mean? When they say the total work done by the engine of the truck to get there is that, then we can, if we're looking at the free body diagram for this truck, right, what are we gonna have here? Normal force, né? Then you are gonna have force of gravity, and then here, what force are you gonna have? Because the truck is going up. For the truck to move up there, guys, there must be the force of the engine, okay? There must be the force of the engine that moves the truck up. And then there is also what? There is also friction, okay? Then there is also friction. So using this information, we can be able to then, try to calculate that height. Right. Now, another thing is this. Height, right? The equation that has height here, when you look at the equations that you are given for work energy and power, the one that has height is the one that is talking about the potential energy. Okay. So, Mina, I would, suggest that maybe you do it this way. We can say the network done on the object. Let's see. I think the last time I was highlighting the fact that you can be using this formula a lot. So maybe we can just say the work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. Please guys, you see this formula is gonna save you in a lot of instances, especially in work energy and power. So what you need to understand about WNC, what is WNC? Is the work done by a non-conservative force, okay? Is the work done by a non-conservative non-conservative force. Now, what is your non-conservative force? The non-conservative forces that we have, there are three of them, and then I usually call them the fat forces. Right? What do we mean? Right? Friction is a non-conservative force. A is applied force. A is applied force, and then T is tension. Those are your non-conservative forces: friction, applied force, and tension. Guys, I don't want to lie to you. I see Mr. Fatai Singh's network is a bit of a challenge. Sorry, sir. I hope that it's getting a bit better. So, friction, applied force, and tension. Guys, those are the non-conservative forces. You are gonna hear this from me, and then you're probably gonna hear this also maybe from your teacher. Ne? What I want you to understand about the topic of work energy and power, please guys, this topic is very, very easy if you just use this formula. Okay, just stick to that formula. If they tell you that you use the principle of conservation of mechanical energy, meaning if you do not have friction, applied force, and tension, that system will be fat free. If you don't have any of these, that system will be fat free. And once a system is fat free, we say it's an isolated system. So if you are dealing with an isolated system, do not worry. Still use the same formula, but just write it first. Ne? Write it first, but then instead of here having WNC, you know what you're gonna write? Just write 0. Okay, just write 0. Why are we writing 0? 0 means we do not have any friction, applied force, and tension. So once you do not have those, please just use 0 there. So you use 0 for isolated systems. But then if the system has fat, meaning if the system has friction, applied force, and tension, just simply use this formula. Then you're gonna be fine. Okay, that's just what we need to do. I hope that is clear. If you manage to hear me there, guys, please just raise your hand so that I know that we are on the same page. Okay, so yeah, so I would like just to reiterate that, please guys, when you're working with work, energy, and power, right, this topic, right, it's one of the most simplest topics in physics. What you just need to understand is that what type of system are you working with? Okay, right? If your system has fat, right, if your system has fat, you can understand fat by fats and oils. A system that is like that is a bit of a complicated system. So any system that has fat, what do we mean by fat? Meaning any system that is going to have frictional force, any system that is going to have applied force, as long as you see that there is applied force there. And when you talk about applied force, we even include we even include the force of the engine. We include the force of the engine. We even include the force of a motor. Force of a motor. We even include the force of a generator. Any force that is applied, okay, all of those are applied forces, okay. And then when you talk about tension, obviously it's if you have a string, okay. Tension is if you have any string or cable or rope, okay. So if you have any string, cable, or rope, it's tension. So any system that is going to have those, right, that is your FET. Any system that is going to have those, it's called, it's not going to be an isolated system. What is the opposite of isolated system? Yeah, there's no opposite, but just know it's not an isolated system, okay? So it's not an isolated system. And but for the fact that it's not an isolated system, we are gonna primarily be using this formula: work done by non-conservative force equals to the change in kinetic energy plus the change in potential energy. This is the formula you're gonna use. Okay, now how are you going to use the formula? It's very simple. If you see that there is friction, here on WNC, you're gonna write work done by friction is equals to change in kinetic energy plus change in potential energy. What if there is friction and also there is applied force? Well, it's simple. You're just gonna write work done by friction plus work done by applied force is equals to change in kinetic energy plus change in potential energy. What if you have friction, applied force, and tension? It's also quite simple. You just write work done by friction plus work done by a force applied plus work done by tension is equals to the change in kinetic energy plus the change in potential energy. Okay, that's just what you should do there. So when we say work done by non-conservative force, we are saying work done by friction or by applied force or by tension. So it depends on how many do you have in the diagram. If you have friction and applied force, have both of them. If you have friction, applied force, and tension, have all of them. Okay, so that is how you deal with a system that is not isolated, which means a system that has FET. Then a system that has no FET, which we usually call FET-free system, a FET-free system, whereby there is no FET. When we say there is no FET, we mean there is no friction, there is no applied force, and there is no tension. For a FET-free system, all of them must not be present. Please, all must not be present. All must not be present. If any of them is present, it immediately becomes a FET, a system that has FET. Once you have applied force, it's no more an isolated system. Once you have tension, it's no more an isolated system. So all of them must not be present for us to call it a what? An isolated system. And this applies to all parts of physics. Okay, this applies to all parts of physics. An isolated system is a system that won't have any FET. So if you do have an isolated system, that means what is going to happen? The first thing is that the total linear momentum is going to be conserved. The total linear momentum is going to be conserved once you have an isolated system. All those problems you were doing when you were doing momentum, if you can go back to all of those problems, they didn't say that there was a rope there. They didn't say that someone was applying a force. When they were giving you examples such as this, you have a gun, right? They were telling you that you have a gun there, and then on this gun, we are firing a shot. And then this goes that side, and then this is gonna go back and stuff, right? There was not really applied force there. We just took them as isolated systems. There was no friction. When we talk about cars crashing, that car A, crashed with car B, right? We do not really focus on the force that they apply on each other. What we focus on is the fact that there is no friction. So we immediately call it an isolated system. And there is no tension again. Okay, so an isolated system is whereby it's FET-free. We don't have friction, applied force, or tension. And also what you must understand is that the um, the law of conservation, the law of conservation of mechanical energies applies also. What does it say? It's going to tell you that um, the total mechanical energy in an isolated system remains constant. What does the principle of oh yeah, so this one here that I said here is the principle of conservation of momentum, right? It's the principle of conservation, the principle of conservation of linear momentum, of linear momentum. Total linear momentum is conserved or remains constant because it's an isolated system. Same with the law of conservation of mechanical energy. You're just gonna say the total mechanical energy in a system is in an isolated system is conserved, or you say it remains constant. Okay, so I hope that is clear. So which formula do you use when you're focusing on work energy and power problems? The formula that you still use is this one. Okay, this is the formula that you still use. However, make sure that here you put 0. Okay, 0 to indicate what? 0 to indicate that you have no fat in the system. I hope that is clear. Are we on the same page? Please do indicate for me again. Are we on the same page? Do we understand when we use fat free and then when we use a system that has fat, meaning friction applied force and tension, right? Great. So we are going to apply that in this problem. I'm going to show you that it works perfectly. So here's a problem here, right? You were told a lot of things about the problem here, that hey, this 10,000 kg truck is traveling up a road of what. Well, you have to just understand that your focus should be what? Your focus should be to tell whether this system, is it a fat-free system or is it a system that has fat? So please guys, can you please just comment for me there whether you think this system is a fat-free system or is a system that has fat? Please comment for me there. Very fast guys, so that we can move. Okay. Um Right. Okay, that's fine. Now, the fact that we do see the force of the engine, that tells you that you are dealing with a system that is fat, meaning because these falls under applied force, right? These falls under applied force, and you have friction itself. So F8 is friction applied force and tension. So definitely you can tell that this is not an isolated system. So therefore for 6.1.1, simply gonna use the formula there. Right, and then now because we have friction and the engine, which is friction and applied force, so I'm simply gonna say the work done by the friction plus the work done by the applied force, which is the force of the engine. So that is my applied force there. And then here, change in kinetic energy is half m, it's half m into vf squared minus vi squared. And then changing that is just mg into H final minus H initial. So the work done by friction, we already given that the work done to overcome friction was 8,5 times 10 to the power 4 joules. But remember, work that is done by friction is always negative work. So I put it as negative there, negative 8,5 times 10 to the power 4. That is the work that was done to overcome friction, right? So that means that is the work done by friction. And then the applied force, they said the work done by the engine was how much? Was 7 times 10 to the power 5. And then you have half. What was the mass of the object? The mass of the object was 10,000. And then what was the final velocity? They said it travels up an incline at a constant speed of 20 kilometers per hour. So the change in velocity there is going to be 0. But it's fine. We can just substitute the speed. And when you substitute that speed, because that is kilometers per hour, you most probably want to put it as how do you turn kilometers per hour to meters per second? How do we turn kilometers per hour to meters per second? If I remember very well, you must just divide by 3,6. Okay, so you can just divide by 3,6. So if you say 20 divided by 3,6, so the answer that you get is like 5,56. Okay, you get 5,56. Right. You see what you're saying there? All right, 5,56. So I'm just gonna put here 5,56 squared minus what? 5,56 squared. Why am I doing that? Because they said constant velocity. Constant velocity tells you that constant speed means that the speed is not changing. So the initial is going to be the same as the final. Then I'm just gonna continue here, right? Plus, what is the mass? The mass is 10,000. And then what is G? Remember that G is 9,8. And then what is the final height? Well, the final height where the object is H, okay? That is the final height. What is the initial height? Since the truck is moving from the ground, then the height at the ground is 0. Okay, the height on the ground is 0. So now from there you can just simply calculate the height. So here when you put it in your calculator, this whole part is gonna be 0, right? So I'm not sure what you're gonna get on that other one, so just gonna quickly do it there. So you're gonna have negative 8,5 times 10 to the power 4 plus 7 times 10 to the power 5, and then you get that is 615,000, and then here it's gonna be 0, and then here you're gonna have 10,000 times 9,8 times 9,8, you get 98,000, and then you put the H there. So that means you're gonna have 615,000 being equal to 98,000 H. So you divide by 98,000 both sides. So therefore the answer that you would get there, so you say 615,000 divided by 98,000, you get 6,23. The height is gonna be 6,23 meters. Then that is your final answer then. 6,23 meters. Oh, sorry, not 23, I mean 28. Oh, why am I getting 23? 28. 28 meters. Right, if there is a question there, yeah, you kindly tell me. 6.1.2. Now we need the instantaneous power that was delivered by the engine of the truck. Now when you're dealing with power, the formulas for power are also there. So when we check power there, when you check these formulas there, power, average power, you can see that it is this formula here, which is force times V average. You can also use this formula here, right? You're also allowed to use that formula, but you can only use this formula if you have the time. The problem is that here they want the power, but we're not given the time there, isn't it? We're not given the time. So if you're not given time, right, so you're only gonna be using this formula here if you have the time given. But if you don't have the time given, then you're probably gonna run to this one, which is this one. So I'm gonna write it here, P average. Ooh, yeah. So let's write it this side, 6.1.2. Now P average is gonna be the force, which is the net force, or just the force, and then times the average velocity. Okay, times the average velocity. Now, what is the force? The force would be the force of the engine, because like the power, when you're dealing with power delivered by the truck, you're talking about the force of the engine, because the engine is the one that delivers power to the truck. So this is the force of the engine. Now the thing is that now to get the force of the engine, that means we do need to get this F applied there. So how do we get the F? Well, we do know that the work done by force applied is this one, right? We do know that the work done by force applied was 7 times 10 to the power 5 joules. Now remember, the formula for work done is FA times change in X times cos theta, isn't it? That is the formula for work done. Now we don't know what is FA, but the change in X, we do know that it traveled 23 meters. So we can just put 23, and then what will be the angle? Since the object is moving in that direction and the force of the engine is also in the same direction, so the angle is going to be 0 degrees. Okay, and then from there you can divide both sides by 23 cos 0 degrees, and then you divide by 23 cos 0 degrees. Therefore the applied force is going to be equal to what? So if you use a calculator there, it's going to be 7 times 10 to the power 15, 5, you divide by 23, so that's going to be around 34,4,78,26 newtons. Now I'm rounding off to 4 decimal digits because it's not my final answer. Okay, it's not my final answer, so I write it like that, and then I say therefore the power, the average power delivered is gonna be that 30,434,7826. Now what is the average velocity? Average velocity, guys, is just the V initial plus V final divided by 2. That is what we mean by average velocity. We're just gonna, it's just V is, it's the V initial plus V final divided by 2. Now we do know that here it was 5,56, like we said, the initial and the final. So we're gonna use 30,434,7826, and then here 5,56 plus 5,56 divided by 2, and then what is the answer that we get? So we say the answer into 5,56 plus 5,56 divided by 2, and then the answer that we get for power is 169 217,39 watts. Remember, the unit for power is going to be watts. And that is your answer there. Yeah, that is your answer there. Yeah, because if we put it in scientific mode, it's gonna be 1,7. Yeah, that's correct. That's correct. So yeah, that's gonna be 169, 217. Yeah, great. 39 watts. So that's gonna be the average power. Right. So I hope that for this topic, it won't be that difficult. Just remember that how to use these formulas. Remember that you're gonna use this one. If ever they say to you if they say use the work energy theorem, they say use the work energy theorem, then you are gonna use this one, and then you know that this one is the one that you're gonna use mainly on almost all the problems, right? Almost all the problems, as long as you have height, or rather you are looking for height or speed and stuff. Because sometimes the object might just be on an horizontal surface, and then it's moving from there to there, right? From there to there, maybe from A to B there. So in that case, the change in EP is going to be 0, because the initial height is going to be 0, final height is going to also be 0. Initial height is 0 meters, final height is also 0 meters, because height is the distance from the ground. So if the object is just on the ground, then this is going to be 0. Okay, so yeah, that's what you're gonna do there. And by the way, guys, this one is a formula we shouldn't forget, for work done by any force. Okay, so it's the formula we shouldn't forget. And then when you're looking for power, this is the formula that you use. Okay, so I hope that the issue of power, work energy and power, has been resolved. Now I'm gonna give you another question just to go through that again, right, to show you that whatever I'm saying, it does apply to actually any situation in work energy and power that you're gonna find. Let me use this one. I like this one because it's gonna be it seems like it's let's see. Let me just check one here. Yeah, let me take this one so that you can see that it does apply to anything. I'm hoping that I will also be able to have time to do this part, because please note that work energy and power, usually they like to incorporate it with momentum. So you need to also be knowing your momentum quite well, right? Those equations in momentum there, you need to be knowing them. Now here's the next question here, just so that you can see what we are saying there. So you have a steel ball, right, of mass 0.5 kg, which is suspended. If it's suspended, it means there's no motion, right, from a string. Right. Now it is released from this point, and then it goes at that point there. Then I'm sure it hits this thing, right? Now, because there's going to be a ball hitting the box, ne? Remember, this should be it is an isolated system because there is no friction here, right? They said ignore the effects of friction, right? So because there is no friction, and this ball is going to hit this one, what is going to happen there? We're going to have a collision. And the moment we have a collision, good people, then you must remember the principle of conservation of momentum. The principle of conservation of momentum. How do you use that? So remember that you're gonna say the sum of momentum before the collision will be equal to the sum of momentum after the collision. So you're gonna say the momentum of this object, which you can call a ball, plus the momentum of the box, okay, initially before the collision, is gonna be equal to the momentum of the ball plus the momentum of the box when finally after the collision. Initial means before the collision, F means after the collision. Actually, you can be able to then calculate there. Okay. The question that follows this, there was 4.3 there, guys. It's asking about that. It's around 8 marks. So I'm already just trying to highlight how does work energy and power, relate to momentum. Whenever there's collision, you must just remember momentum again. So, but then here, the focus here is that this thing is moving from here to there, to C, A, B, C. We can also take this as an example of the pendulum. Okay. So 4.1 it says, write down the principle of conservation of mechanical energy in words. Very easy, guys. You just have to say what? The total, whatever they told you, the total mechanical energy um, in an isolated system is what is conserved. That's it. Okay, and then calculate the mechanical energy of the steel ball at point B. So we want to know what is the mechanical energy of the steel ball at point B. Now, mechanical energy, which I always use me, right, as an abbreviation. Mechanical energy, which is ME, it is equal to the sum of potential energy and kinetic energy. So it's kinetic energy plus potential energy. So how do you use the conservation of mechanical energy? You usually have to say mechanical energy at point A is going to be equal to the mechanical energy at point B. This is how you use the mechanical energy. So what are you going to say there? You're going to say kinetic energy plus potential energy at point A is going to be equal to kinetic energy plus potential energy at B. Okay, but if this formula seems like, since it's new, it might be a bit difficult for me, then don't worry. What you simply have to do there is to use the formula that I gave you before. Remember this formula, WNC is equals to change in KE plus change in EP. Remember this formula, use it again. But then because we are dealing with an isolated system here, whereby there's no friction, applied force or tension, don't consider this as the tension though, because the tension doesn't, this string doesn't really have any effect on the mechanical energy, okay, on the energy of the ball there. So do not consider that string as taking an effect per se, okay. You just take this as an isolated system because you don't have friction, you don't have an applied force, mainly because the object was released. No one applied any force, it was just released and then it went down on its own. So they said to us, right, as it passes through point B, which is 0.6 meters above the ground, the magnitude of the velocity was 3 meters per second. We are going to need that velocity there, the velocity at B. So we shall take that as final velocity, and then we shall take the velocity here initial as 0 meters per second because the object was released. That means it had zero, it was at rest first. So when you release it, the initial velocity is 0. It's more of like when you drop an object, it means the initial velocity is 0. So it's going to move from A to B there. Now, how do we use this formula? Just substitute 0 because we are saying it's an isolated system. Then this one here, remember, it's half m vf squared minus vi squared. And then this one, remember, it's mg h final minus h initial. Now, the mass of the object is what? The mass is 0.5 kg. Now what is the what actually are we doing here? You will see that we do have the height here, but we don't have the height of the initial, like we don't have the initial height, because the initial height is the height where the object is at A. So we don't have that initial, but we do have the final height, that it was 0.6, because we're focusing on point A and point B. So we do know the height at B, we don't know the height at A. We can call the height at A initial height. So final velocity was 3, so I'm just going to put 3 squared. What is the initial velocity? It's 0 squared. The mass is 0.5, and then here G is always 9.8. The final height we were given as 0.6, but do we know the initial? No, we don't know the initial, so we can get the initial height. Okay. And then but now I'm worried. Getting the initial height is okay and all, but now I don't think it's gonna answer the question, because the question was the mechanical energy of the steel ball at B. And if that is the case, that means we're just looking at me at B, which is simply kinetic energy at B plus potential energy at B, which means half mv squared at B plus mgh at B. Okay, so the mass is what? The mass is 0.5, and then the velocity at B we had already been given as 3, and then the mass is 0.5, and then G is 9.8, the height at B is 0.6. So actually this is just a straightforward question, guys. You can just use this formula, meaning you can just calculate the mechanical energy at B, because that's what they wanted. I thought they said at A. Yeah, for some reason they must make sure you read the questions properly. But yeah, this is quite an easy one. For me as an examiner, I would actually be asking you at A. But if they wanted at A, this is what you would do, guys. Whatever was applying here, this is what you do, so that you get the initial height there at A, then you'll be able to get the mechanical energy at A. So let's actually do that. So we're gonna have 0 is equals to, what is going to be the answer there? It's just a matter of you putting that in your calculator. Have half 0.5, and then into 3 squared minus 0, and then plus 0.5. Oh yeah, just want that part. So it gives you 2.25, and then you say plus 0.5 times 9.8, it gives you 4.9, and then here you have 0.6 minus the initial height, I mean. So then you can say minus 2.25 will be equal to, now when you multiply this and that, you just do a bit of distribution there. 4.9 multiplied by the 0.6, you get 2.94, and then 4.9 times that will be minus 4.9 height initial. Then you take this to the left, then you're gonna have minus 2.25 minus 2.94. What is the answer that you get? Minus 5.19 is equal to the negative 4.9 h initial. You divide by negative 4.9 by negative 4.9, therefore the initial height is gonna be what? So you say 5.19 divided by that 4.9, you get 1.06 meters, which makes sense. So your initial height there, guys, we get it as 1.06 meters. Now that you will have the height at A, right? Now you can actually calculate the mechanical energy at A. So what will be your mechanical energy at A? it will simply be mechanical energy at A will be the kinetic energy at A plus the potential energy at A. I usually just say me keep. If I say me keep, it reminds me of what is mechanical energy. It's just kinetic energy plus potential energy at that particular point. So yeah, so that means we're dealing with half mv squared at A plus mgh at A. So what is the mass? The mass is 0.5, and then what is the velocity at A? Remember, it's 0, right? And then what is the mass? 0.5, and then g is 9.8. What is the height at A? Is the one that we just found there, that it is 1.06, so we put 1.06. Then in that way you'll be able to get that as what, 0.5 times 9.8 and then times 1.06, so you get it as 5.19 joules. Measure it in joules. Okay, so yeah, that's what you get. That's the mechanical energy at A. So yeah, 4.2 guys, it was a straightforward question asking you to get mechanical energy at B, right? Which I didn't really get. Why was it really 4 marks, But yeah, that's what we have there as the mechanical energy at B. You just put this in your calculator. But then if you wanted mechanical energy at A, you would go through this process here to get the height at A, and then you substitute it here to get the mechanical energy at A.